Thank you very much. Thank you. Yeah, so this is like all the work is joint work with folks from MSR, Windows, and M365, and it's all about formal methods in the sort of this new world. And let's grab some common ground. So we all love PL. PL is a part of computer science. It's all about reasoning about programs. So we say, but actually what we care about is there a bug in my program? Yeah, so it's all about finding bugs or proving that there's no bugs. And we look what was happening at Microsoft over these decades. So first we were looking at bugs in device drivers, because that was the Windows era. Then we were looking at bugs in in our cloud configurations. That was the kind of PGP verification era. And now there's this AI era. And so the question is like, what's the story going on there? So, and some people think that this focus on AI efficiency could be actually worth looking at. And one of the reasons for that is because everybody knows this. So running this LLMs is actually very, very expensive. So the CapEx, GPUs are expensive, and also they consume a lot of electricity. So, and one way to think about all this is to say, okay, so there might be a different opportunity for impact for formal methods. So like expanding from this question, is my program correct, to this question, how can I run my program in a more efficient way? So, and automation is what we all love, how to make this optimizing compilers, runtimes, and so on and so forth. And it feels like PL verification is really providing foundations, and this is absolutely the crowd. So, and I believe this is kind of where the common ground starts ending, and let's look more closely at what the AI workloads look like and what could be the challenges there. So we, of course, over decades, we've been looking really hard at things like loops, data structures, concurrency, like all this tricky stuff, memory models. And these challenges are not going away. But there's this new workloads, and these workloads, they run on very distributed, very parallel hardware, basically GPUs packed in clusters, packed into data centers, and so on and so forth. And optimization is really important. It's really trivial to run PyTorch on a GPU. It's just going to be horribly inefficient. Efficiency is really key. And there's a new kind of computation. So it's no longer things that we looked so far, like C, C++. So it's all about tensors. Basically, think of it as arrays that are we pretend to be n-dimensional. So it's all about tensor computation. So very basic from a certain perspective, but that's what these things do. It's like most of the time actually goes into essentially matmuls and similar things. And and it feels like if we can expand to compute that touches these areas, actually we can cover even bigger ground with PL and verification techniques. Oh, this is dramatic transition. So I just copied it from somewhere. So with the transition. So another thing actually, and kind of resonates what Alistair was mentioning in his presentation before, is that this whole notion of correctness, it's like becomes, ooh, what is that? So they're very used and love this notion of correctness when we say correctness means, like satisfaction relation. You have a model, so represented as traces, represented as BDDs, represented as source code, and you have the property, logic, assertions, like you name it. But there's something usually in discrete math, so you can formalize in Lean and Coq, in Hoare logic, whatever. And that's the specification of correctness. So if you move to the world of LLMs, we still have the phi on the right, yeah? So it's a joke. So phi is a model from Microsoft. But when you talk to folks who actually ship this model, actually put it into production, so what they care about is that the model performs well on the benchmark data sets. That's basically what it's all about. This is a tech report for the 5.4, like the most recent model trained by Microsoft. And essentially, this is page one. So we train this model, this is how it performs. And that's what the goodness, think of it as correctness, functional specification, all these great things is basically encapsulated by this model. And now, whatever you do with M, actually, you want the, all these scores to be great. So another angle here is that traditionally we think about efficiency as like running fast, like burning all the cores, or sort of using not too much electricity, sort of, or running on fewer GPUs, on smaller GPUs, sort of. But this is just one angle to it. So the other angle is because sort of all this AI is moving so fast. Actually, sort of velocity or just rolling out things is very, very important. So this is another dramatic effect. Maybe some of you have heard of, like in January, so there was this DeepSeek model. Yeah, it was actually quite disruptive for OpenAI models. And so you can imagine that then everybody sort of rushed to say, oh, we can offer DeepSeek for you too. And then sort of offering a model on a platform requires, like, quite a bit of, think of it like deployment, compiler work, this kind of things. And sort of it's a very high priority for all these cloud companies. And yeah, so like if you don't roll out quick enough, sort of you miss the wave, and then sort of, yeah, not great things are going to happen. So another interesting thing that's actually happening now, and a little bit also what Alistair was saying is that, so like a couple of years ago, sort of ChatGPT was all about cloud GPUs, and so you would run these huge models, or huge for the day, sort of on cloud GPUs that cost a lot of money, sort of nobody can buy them, and sort of NVIDIA is just selling shovels. And sort of what happens over the couple of years is that models actually, so on one side became more capable, on the other side, sort of the state-of-the-art capabilities, now you can pack it into much smaller models. Yeah, you don't need to have like all these hundreds of gigabytes of weights. So like tens of gigabytes of weights is actually good enough these days. And this opening interesting application possibilities for running the models, not in the cloud, but on the edge devices, like your laptop, your phone, all these kind of things. What it means actually, it requires even more sort of tooling to bring models to the edge devices. And so this is kind of zooming into where I want to go in this presentation. So so traditionally, when we think about LLMs, we think about sort of the NVIDIA GPU. So the cool thing about it, besides all the compute, is actually a lot of HBM. So this is this high bandwidth memory to push the tensor data in and out, sort of from memory to compute. It has 80 gigabytes of it, or even more, sort of depending on the model. So when you think about running models locally on something like a laptop, actually there is no HBM. So compute is kind of restricted. So there are not even floats. So you need to do your tensor computation in integers. So you don't have floats for tensors. And actually you don't have dedicated memory, because memory is actually very power hungry. So what you want to do is you have your laptop memory, like 16 or 32 gigabytes. And that's actually what your NPU, sort of this neural processing unit, sort of the tensor sort of core processor, if you wish, is going to use to store the weights to run the model. Yeah, and sort of now sort of challenges are, so you have these big models, so you have the smaller models, but then even 14 gigabytes, if I load it here on this laptop, it basically there's not going to be any space to run applications that would use the model. So, and so like zooming right in, so I really apologize now, it's becoming really annoying, sort of these smooth transitions. So I'm going to talk about it at Aqua. So a tool that we've built over the course of kind of the last year, that actually, so to think of it as a compiler pass. So what it does, it takes a model that was trained on the cloud GPUs and floats and all this kind of things, like with high precision, and then sort of it shrinks it in order to be able to run on something less capable. And sort of one of our application areas is the AI Copilot Plus PC, basically sort of the laptops with NPU. And it's all about actually building this tool, so that's what I'm going to talk about. So with one thing to remember from this presentation, it's all about Carrot, it's a quantization algorithm, and Aqua. Automatic quantization is the name of the tool chain. So just a sort of little sense in the background. Who of you heard about PyTorch? Oh wow, this is amazing. So Popple last year, so I was like grabbing the snacks at the reception and asked like PyTorch. So like very few hands. So this is amazing. So yeah, PyTorch is the future. So okay. So our goal is to take this big model and sort of shrink it to run on the NPU, so on the small consumer device. So how we do it? So we use this technique called quantization. So quantization is like as a fancy word for compression that goes over many different dimensions. And so essentially what you're trying to do, you're trying to shrink the memory footprint, and also you're trying to shrink basically the amount of compute you need. So basically you go after memory and latency at the same time. And sort of usually it's done by reducing the width of the data types. For example, if you were to train the model like in 16-bit floats, you would go for 8-bit ints, or so things like even 4 bits. So the holy grail is like 2 bits or like 1.56 bits, like crazy things like that. So it's very exciting, this whole quantization area. And what you shrink is, you shrink the weights. Basically, this is the thing that you actually obtain by training. This is the thing that you measure in gigabytes. And then you shrink activations. These are basically tensors that your model, basically think of it as a program state that gets evolved as your PyTorch crunches the tensors. And KV cache, this is the thing that you, basically think of it as a prefix of the history of the model interaction, sort of all the stuff that Alistair was showing about, oh, I talk to the model, it gives me this answer, and then I say, oh, no, you were wrong, so do something differently. All these interactions so far, they're kind of accumulated, and sort of that's called the KV cache. So all these things shrink, and sort of you obtain some gains. For example, like obviously if you go from 16 bits to 4 bits, you get a 4x on memory. And then also, because most of the operations are matmuls, you know that matmul is quadratic in the bit width, sort of you get advantages. And there's a whole range of quantization methods. You can imagine sort of this is kind of the holy grail of one branch of machine learning, is basically how to quantize the models, because like so many knobs to turn and so many sort of scenarios to specialize for. So one quantization method that we particularly care about is called caret. So it's a quantization / rotation. And this is a state-of-the-art, one of the few. So, and sort of what makes it very interesting is like, it's a good fit for NPU sort of offload. And mathematically, so what's going on here is that we say that given a tensor that we want to compress, so you do a transformation on the tensor, which is called rotation. And this rotation removes outliers. So if you think about, zip on text, imagine sort of you have a file that has a single word in it. Yeah, so this file is very easy to compress. Yeah, so dictionary size 1, just this word, so many repetitions. If you start introducing diversity in your text file, you start introducing different words. So basically, yeah, so it's becoming harder to compress. And you can think of basically every time you introduce something new, think of it as you're introducing an outlier. And sort of, so what this rotation trick is doing is basically saying sort of a tensor is basically an n-dimensional vector. And sort of if you plot the numbers so they have like different height, and outliers are particularly tall numbers, and rotation matrix actually sort of will make sure applying rotation that those outliers kind of smooth out. So that's the mathematical trick. And sort of you apply this rotation, then you quantize, then you unrotate, and then sort of it has beneficial effect on the quality of models. So you can shrink and without losing too much precision. So applying this rotation is kind of not trivial, so like most of the things that we do when we transform programs. So why automating this is, it feels like sort of there's like only 1-2 models out there and sort of it can do it by hand, but actually some models keep coming, sort of everybody, well, like there are many teams in the world that train models and different varieties of models. So basically there's a stream of models to quantize. So models themselves is a software artifact. So there's a software updates in the like libraries, infrastructure, software stack that uses them. And also like quantization algorithms, sort of new quantization research sort of produces new algorithms. So basically you really want automation. You don't want to do these things by hand. And another thing is like if you squint and look at the state of that in quantization research, because a lot of work is done by hand, basically it's not great for the research area because it's difficult to compare things, difficult to evolve, all this type of stuff. Yeah, by the way, sort of transformers is, think of it as a libc in the world of C++. Transformers is the equivalent in the world of LLMs. So this is what Hugging Face hosts you. That basically you give a name and you get the source code for a model plus the weights. And sort of you change version of transformers, boom, sort of your model source code changes and sort of all the quantization work you've done on the previous version of transformers you need to throw away. Basically, yeah, compiler type tools are really important here. So now sort of getting a little bit more into sort of this PL world. So if you step back, we can say, okay, sort of this quantization algorithm is a basic combination of two steps. One is local rewrites, where every operation in the graph that produces a tensor, you say, oh, what if I were to quantize this tensor? Basically rotate, quantize, and rotate. And sort of you introduce all these operations, and then you say, oh, I have this modified graph, and then sort of let me have a global optimization pass over it. And basically sort of, this is our perspective, like what we obtained by reading the paper that describes Caret, and sort of that was the starting point for our automation journey. And sort of in the next couple of slides, I'll just give you a little bit of, examples, what this two-step means, and sort of how would you proceed in building an automatic tool using like PL techniques. So everything starts with the graph. Sort of this is a data flow graph. So there are ops, and sort of there's data flow between the ops, like as you would expect. For practical purposes, just think of it as SSA, yeah, data flow graph. So you pick a couple of ops, and now we can sort of do transform on this ops, sort of applying the quantization algorithm. So one important op in PyTorch is the add sign, which is matmul. So basically that's the expensive one. The star is the pointwise multiplication, that's cheap. Matmul is the expensive one. Excuse me. So, okay, say we have this operation sort of that produces FP16 tensor, and then there is some op2 that consumes this tensor in FP16, and that's very slow. So what we would like is to turn the op2, the downstream op, into something lower bit, like int4. And so we want to transform the output of the predecessor op using this Caret thing. So what's going on here is like literally as I described before. So we take the incoming tensor, we rotate it, removes outliers, then you quantize it, basically rescale and do all these kind of things, because there are no outliers. Sort of numbers are all like very close to each other. Sort of there's not much loss during the quantization step. And so I think this is the point where Ali said, oh, slightly correct. Yeah, this is not much loss during quantization step. And so we move on with the transformation. So then basically data is rotated, so it's semantically sort of different. So you need to unrotate, apply the unrotation thing, and then hope so that you get your info data. So this looks like fantastic from the perspective of correctness, like if you squint it, almost the same. But from the perf perspective, it's actually quite bad. And so one of the reasons for that is rotation operation. So if you go back to computer graphics class or anything sort of from the high school, rotation is actually applying rotation matrix, and the rotation matrix is a matmul, and we just said matmuls are the expensive things. And what we are doing, we're saying, okay, if op2 was a matmul operation, so we can actually do it with lower precision by checking in 2 additional matmuls. So that kind of doesn't make sense. So bear with me. So there is hope. Yeah.
When I think about high school rotation matrix, I think of a 3x3 matrix. Are these multi-dimensional tensors or rotation matrices, and then some large n by some large n size? Or?
Yeah. So very good point. So the dimension is basically thousands, and sort of in terms of LLM, this is number of heads times the embedding dimension. Basically, in the tensor, you rotate the last one, basically the semantics, the embedding. Number of heads times the hidden. Basically, 128 heads times like 128 or things like that for a small model. But it's a big matrix. And by the way, there's a fascinating theory and practice on these rotations. For example, there's this Hadamard rotation, there's this rotation. Some of these rotation matrices are actually a Boolean, so there are zeros and ones. And then the matmul is actually can be done in n log n instead of the matmul cost. So the fascinating world, basically, it's really cool. But sort of for our purposes, like from more like discrete math perspective, we introduced 2 matmuls to sort of simplify one. So now sort of the full power of compilers comes in and says, oh, so Fusion can eliminate sort of things from online and push it into offline. So only if we could fuse. And essentially sort of that's, so if you look back at this sort of tool chain we've built, it's all about actually fusion. And you can think of fusion actually, it's all about figuring out commutativity of ops in the graph. And then because once things commute, you can put them together and fuse and all this kind of stuff. So examples are coming, but sort of high level point, it's all about fusion. So here's some examples. Say this op1 is a matmul. happens like 4 times per self-attention layer. So there's a couple of things. So op1 is a matmul. So often these matmuls actually take an activation X, something that actually encodes your string embedding, whatever sort of what you are processing, generating. And the second argument very often is weights that you have sort of obtained from training. So basically weights are constant. Yeah, so in this case, so if you have op1 matmul followed by the rotation, which is a matmul, so what we do is that, okay, so this is the almost equality, yeah? So basically an optimizing compiler like, C, C++ and sort of Fortran libraries for it would never claim that, oh, you can actually sort of put the parentheses in a different way because numerically the results are going to be different. Yeah, so like big no. But from the purpose of like this quantization sort of optimization, so it's good enough. So actually, instead of equality, sort of PyTorch usually uses all close, and then you have the knobs on how close things supposed to be. So and essentially now what happens is that, yeah, so you can sort of move the parentheses or out a sort of somewhat more general way of thinking about it. You can actually commute this operator. So, and then you pre-compute W times Q offline. You store it on disk and sort of, yeah, you don't need to do that matmul. So this is one of the tricks. And then sort of you can also imagine that sort of in the actual model, so between op1 and rotate, there could be like a whole bunch of other ops. And then sort of the tool needs to figure out, oh, there was an opportunity to fuse this matmul and that matmul. So can I actually commute and bring them together? So another one is actually it's like somewhat more sophisticated example here. So imagine, so the op2 actually commutes with the rotation. So then so there's a very simple rewrite because of the commutativity. You can push the unrotate, so they come together, they cancel out, so you remove it. Okay, so this is another sort of trick that's been used. So all of this is actually leading up to this slide, which is again from the formal purification perspective is like testing, theorem proving. What do we go with? Also a little bit, I think sort of actually, Alistair, all your stuff on sort of these untestable things was like, like music to my ears. So basically sort of to move things around in order to fuse, we need to essentially to prove this universal statement, or this universal missing, like for all x, if I run an op and then unrotate, it's the same as like unrotating and then running the op. Basically you can f follow g versus g follow f, like commutativity for all inputs. And sort of in a world where you have a programming language that's been around for half a century, and sort of many people sort of invested in understanding the language and writing down semantics for the language and for hardware on which you run it, so you can sort of go and prove these theorems, but sort of pragmatically, so for all these GPUs and sort of PyTorch and some ops that keep coming up, actually we don't have that luxury. And sort of what we do, we just test. But sort of there's a trick, it's an amplified testing, and sort of there's a hypothesis is that sort of for the ops in these models, sort of the control flow in the kernel, basically in the code that actually implements the matmul or whatever, is not going to be data dependent. So it only is determined basically by the tensor shapes plus flags to the kernel. What it means is that actually if you fix the shape of the tensors, you can slap a universal on the sort of on the content of the tensor. And sort of we're thinking about some sort of PTX analyzer to prove that there is no flow from the data of the tensor into control of the PTX code. So basically we do testing. So testing is amazing, and sort of no formal spec required, sort of hit the ground running. So and sort of that leads us to, I think, close to running out of time and the optimal program synthesis problem. So as I mentioned before, so we are going from proving correctness into sort of making things faster, which means we're going from satisfiability to optimality. So that's why optimal program synthesis. And then sort of if you squint, sort of what we're really figuring out is like given this data flow graph, so pepper it up with this rotation and quantization instructions somehow in such a way that sort of things will run with smaller bits. So they will fit into the memory sort of available on the device, and all subject to the fact that to this condition that actually when you place these instructions, so they're going to make things more expensive, but sort of they have potential to be fused. And sort of that's what we also pre-compute, that if I were to put a rotation here, would I be able to fuse? That's sort of part of the constraint system. And so we cook that soup, and then sort of it's how it goes. So from the, like static analysis or like any compiler perspective, it's pretty much standard flow. So we take a PyTorch module, so like trace it, get a graph. So graph is basically, that's something that then like NVIDIA sort of so would take over to execute on the device. Sort of we generate constraints, like standard static analysis approach, take the IR, generate constraints, do some probes on the cost functions of all the individual things, figure out what can be fused if it was to be inserted at different points in the graph. We do solving. So then it puts out a schedule. So basically do and implement the schedule, sort of do the operations, produce the graph, and then you can offload. So that's the story. Any questions at this point? No. Yes.
I have a couple of questions. This rotational operation that you described, is it something that happens at inference time or at training time or fine-tuning time, or what time of the pipeline does it happen?
So this is post-training quantization. So basically the model is already so-called pre-trained. Basically the big weights are already there. So the sort of a naive approach with this rotation would be you insert them in the graph, and you can do inference with it. Of course, sort of you pay the price. So basically, they only make sense if they actually can be eliminated through fusion. And sort of that's sort of, think of it as basically the pre-processing time before you deploy into production, before inferencing.
And the second question I have is, it has been studied a number of times where quantization for anything less than 16 bits comes with a pretty significant drop in accuracy. And so do you have any special insights on embeddings that would actually prevent this from happening?
I don't know about what you mean by embeddings, but so that I can tell you numbers sort of the bit widths sort of that we use. So basically weights are 4 bits and activations are 8 bits ints.
Thanks.
Yeah, so we can talk offline on sort of particularities. Okay, so yeah, this is the pipeline. It's amazing. So PyTorch, by the way, is actually the very exciting sort of playground if you love sort of, poking, sort of going this journey, program, source code, IR, because it starts from Python. So PyTorch is essentially Python plus libraries. It's like systems Verilog is C++ plus libraries. And but because it's all Python, everything is dynamic, and yeah. Okay, so the grand finale. So improving AI efficiency, I believe it's kind of the opportunity of our time. So 4PL research, for verification research, because it looks like it's just, so you can do all the great things you've been doing so far in sort of learn and sort of advance, plus so all these workloads that sort of, it looks like, so they just keep expanding, and it's a very interesting. This is just just one tiny step in this whole journey. So how you take the data, sort of design architecture, train it, and then sort of ship it to production, deploy on the device on cloud GPUs. Like so much work there. It's all very exciting. So another exciting bit sort of here is that so basically you don't need to deal with sort of whatever the universe throws at you, like some arbitrary like C code. So it's kind of relatively sort of understood, so set of inputs to your tool chain, so you can go and sort of specialize and optimize for this particular sort of inputs, which makes it also very interesting. You don't need to spend a lot of time sort of trying to figure out sort of how do I build a parser for anything that moves under the sun. Cool. Thank you very much.
Ali in the back.
Thanks, Andrey. Really interesting. I had a question about your last comment, which was actually, you made the point you don't have to be, your toolchain doesn't have to work with anything under the sun. It can be quite limited in what it's going to expect. I actually wondered how much it's even the other extreme, because when people talk about next models, I always hear like the focus is on data. To what extent are there really interesting model architectures, and to what extent are they getting more or less interesting or changing versus the kind of architecture of these models being now pretty stable and it being much more about retraining them on new data?
Oh, thank you. So it's I think sort of the amount of change is very much in the eye of the beholder. So if you talk to ML people, they say, oh, but instead of like something like many letter acronym, we have this other mean. It's a completely different architecture. It's like, okay. So we changed from square root to like sine or whatever. It's like, oh, from the graph perspective, it's like, okay, so so from the machine learning perspective, like for them, these are big changes. But also there are sometimes for like significant changes that you spot them even on the data flow graph. For example, DeepSeek actually has a significantly different attention mechanism, and so the way they use KV cache, basically it doesn't grow with the sequence length. So basically, big changes. That actually was one of the parts of their disruption. So everybody thinks like, oh, like everything has been innovated to the max, and then boom, sort of new things come up. The other thing here is that it's a little bit of like 1,000 cuts problem. So things are slightly different, and sort of for the automation, sort of it's very good. So I think from the perspective of like if you're a new researcher who wants to invent new architectures, I don't know if it's been exhausted or not, but at least from the tooling perspective, there's enough diversity.
Very interesting. I guess I was wondering whether there is scope for super optimization. You know, in traditional compilers, there's been work on super optimizing programs, but it's very expensive to do. And if your program is going to change, there's no point having super optimized it. But I wonder whether there could be scope for some super optimization to make inference be really efficient.
Yeah, actually, it's a very good point. So like the work I presented here is more on the graph level, basically individual ops. But as I mentioned, sort of it's just one sort of slice through the lifetime. So also like one slice through the vertical in whatever dimension. So basically from the graph, you go to kernels. Kernels get fused. Basically, you get the PTX. Think of PTX as like is the last thing you see before like CUDA takes over. And sort of there's a bunch of work so actually trying to figure out how to do optimization, different optimization approaches, including super optimization for PTX. And yeah, so it's a very great opportunity for your research. Yeah, so tons of opportunity. Also, like just one more point in this. Basically, some of these models, basically, they serve humongous workloads. Like even small percent point improvements on those kernels are going to save a lot of electricity.
Okay. Thank you so much, Andrey. I think there might be other questions, including from myself, but in the interest of time, we'll come and pass to you in the break.
Like our old friendship warrants you a question. Or maybe offline.
Thanks very much. Let's thank Andrey again.